So now we're going to return to geometric group theory, and I want to explain the proof of this theorem here, which, as I mentioned before, implies these four problems of Thurston on the circling around the virtual Haken conjecture. Sorry, I'm going to have to skip through the feature manifold stuff that is discussed. So now I need to say a few more definitions. So if we have a collection of subgroups H1 through Hm of a group G, then it's called almost malnormal if the intersection of a conjugate of Hi, so Hi upper G means that you conjugate Hi by some element G. If that intersects one of the Hj's in an infinite subgroup, then that implies actually that I was equal to J and that G was actually inside of Hi, so that we were just intersecting Hi with itself. So in other words, if you take the contrapositive, then that's saying that if I take a non-trivial intersection of Hi in some Hj with I not equal to J, or conjugate of Hi with a conjugate of Hj, I not equal to J, that intersection is always finite. It certainly has to contain the identity element, but it's always finite, is another way of saying it. And if I intersect Hi with any non-trivial conjugate of Hi, then that intersection is always finite. So that's sort of the contrapositive way of saying it. So there's a theorem of Bowditch that says that if you have G a hyperbolic group and H1 through Hm a collection of subgroups, then G is hyperbolic relative to H1 through Hm if and only if Hi is quasi-convex. So I explained quasi-convexity yesterday, and they form an almost malnormal collection, so it's satisfying this definition. Now I haven't explained what relative hyperbolicity is. So I gave a brief definition of what a hyperbolic space is. So a group is hyperbolic if its Cayley graph with respect to a finite generating set is delta hyperbolic for some delta. So it's got delta thin triangles. Relative hyperbolicity is a little bit trickier to say. Inside of G, we can take these subgroups and that are finally, we'll take some generating sets for them. So what you can do is you can cone off those Cayley graphs of the subgroups inside of the G, and you cone off all their cosets to a point, and that should be a hyperbolic space. Now that's actually not quite relative hyperbolicity. There's a sort of weak version of relative hyperbolicity that that's equivalent to. So what you do is instead of just coning it off to a point, you maybe I'll try to draw a picture. So just schematically, if you have the Cayley graph of G, so let's say this is the Cayley graph of G, it's some blob, and then you have this subgroup H, let's just take one subgroup H, or H1, and then there'll be all these cosets of H1, and they might cross through each other. So instead of just coning it off to a point, which is weakly relatively hyperbolic, what you do is you sort of take a warp product of this. So you take an exponential. So you take a product with R plus, but you warp this so that the metric on each cross section. So this is H1 crossed with T is e to the minus T times the metric on H. So it's a warped, an exponential warp product, and you attach on these things, and then this Cayley graph, or you can take anything quasi-isometric to G. You know, G acts co-compact around some space. You can just do that. You attach on these things, and that should be a delta hyperbolic space. Is delta hyperbolic for some delta. So that's what relative hyperbolicity means. If you have a hyperbolic 3-manifold, then with finite volume, then it might have these rank 2 cusps. So it's not actually a hyperbolic group. But if you cut off those cusps, so you neuter the space, is what Rich Schwartz would call it, then you get something that's quasi-isometric to the group. But now it's no longer a hyperbolic group because it's got these flats there corresponding to the boundary of the cusp. But if you put the cusp back in by this exponential warp product, then you just get back hyperbolic space, and now your space is delta hyperbolic. Any hyperbolic space is delta hyperbolic for some delta. So that's sort of where this relative hyperbolicity notion comes from, is thinking about non-uniform lattices in hyperbolic space. They're not actually, their fundamental groups are not delta hyperbolic, but they are hyperbolic relative to their peripheral subgroups corresponding to the abelian fundamental groups, or virtually abelian fundamental groups of the cusps. So that's where this relative hyperbolicity notion comes from. So examples of malnormal subgroups: if you have a hyperbolic group, a delta hyperbolic group, and you take a collection of elements of infinite order in it that are primitive, so they're not proper powers, and they're not conjugate to each other or any power of each other one, then those will form an almost malnormal collection of cyclic subgroups. So if you have these cyclic subgroups, you attach on these, you can imagine that G is like a surface group, and you have these immersed curves on it, and you sort of cone those off exponentially warped products, then that space will also be delta hyperbolic. So this picture almost becomes a literal picture in that case. So you can think of it like a hyperbolic plane and coning it off by a bunch of lines. That will still be delta hyperbolic for some delta. The delta will depend on which collection of curves you've chosen. But that's sort of an idea of what relative hyperbolicity means. So I'm not going to I'm just going to state a theorem that holds for relative hyperbolic groups. So I'm not really going to go into that much, which is I'm not being too precise about it. So the Wise's malnormal special quotient theorem is a little bit technical to state, but it says that if you have a hyperbolic group which is hyperbolic relative to a collection of subgroups, so H1 through HM is malnormal collection of quasi-convex subgroups, then there's finite index subgroups HI dot normal in HI, a finite index, so that for any HI prime in HI dot, the quotient group G bar, which is G, and I kill off, so by these double brackets here, I mean take the normal subgroup generated by those collection of subgroups. That's a virtually special hyperbolic group. So it's kind of a mouthful. It's a little bit hard to parse.
Which are finite index subgroups?
The HI dots. Yeah, I forgot to say that in the statement. But the HI dots are finite index in HI. And HI prime, sorry. In the statement of the theorem, HI prime should also be finite index in HI. And you may as well assume they're normal in there too. So there's a relative version of hyperbolic Dane filling result that's due to Groves and Manning and independently due to Osen. Osen's version, slightly more general, can deal with torsion, and actually we have to make use of Osen's version in our in the proof in a slightly different context. So you can conclude that G bar is hyperbolic whenever HI mod HI dot has, I'm going to call it large girth, but this is saying that if I take HI and I take its Cayley graph, then when I take HI mod HI dot, the Cayley graph quotients to a finite graph, and that graph has large girth, meaning that if you take any ball in the Cayley graph of HI, that ball will embed down into the quotient Cayley graph, a ball of a certain large enough radius. So this is called relatively hyperbolic Dane filling. It's really a descendant of small cancellation theory and sort of also of Thurston's hyperbolic Dane filling theorem for cusp hyperbolic manifolds, if you're familiar with that. Now the difficult thing here, and also what happens is when you kill the HI primes, if these guys are normal actually in HI, then if I look at the normal subgroup generated by that and I intersect it with any of the HIs, I just get precisely the thing that I'm killing. So this happens, like, for example, in hyperbolic Dane filling. When you do a Dane filling, maybe I'll draw another picture, on a cusp hyperbolic manifold, then it has this just just by analogy, if we take, for example, the figure 8 knot and we do a P over Q surgery on that, then it's hyperbolic relative to the z squared subgroup. There's a z squared subgroup, the boundary component there, and you attach in a solid torus to the P over Q curve sitting on here, then the point is that when you do that for all but finally many P's over Q's, the core of that filling will be will inject into the quotient group. So when you do the Dane filling, the Seifert Van Kampen says that you just take this group and you quotient by whatever the peripheral element that is bounds of disks over here in the solid torus. But the core of the solid torus will be pi1 injective in Thurston's hyperbolic Dane filling theorem for all but finally many P over Q. That holds true by Thurston's hyperbolic Dane filling theorem. And so there's a similar thing going on here, that you're killing, inside of HI, you're killing precisely what you expect to be killing, as long as these guys are normal. So the statement of the theorem doesn't require normal, because you might just end up killing, you're killing the normal closure then. So that's one aspect. To show that these guys are hyperbolic is this hyperbolic Dane filling theorem. The difficult part of this theorem is showing that the quotient is virtually special. And this, so it's sort of indirect. So Y shows that there's virtually a malnormal quasi-convex hierarchy, and then applies his joint work with Hagelin and Shu to conclude that it's virtually special. And this is really, this is proved on page 120 of this 180-page paper, and these other two papers with Shu and Wise is another 40 and 20 pages, so another 60 pages or so. So it's really hundreds of pages of mathematics that go into the proof of this theorem. And when you see it, it might not be that that obvious what the power of it is, or why it's useful, or even what it means. But even in the case of a free group, this is a non-trivial theorem. So if you take a free group, you take a bunch of elements inside that free group, which are and take the cyclic subgroups generated by them. This is saying if you kill high enough powers of those elements, that the quotient will be a virtually special hyperbolic group. So it will act properly co-compactly on a cube complex. There's a finite subgroup that acts specially on that cube complex. So that's a non-trivial theorem. So now I want to talk about the proof of the virtual special theorem. So the proof of the theorem is by induction on dimension. So you let X be a compact, locally cat0 cube complex. G is pi1 of X is a hyperbolic group, delta hyperbolic. And inside of X, there's these hyperplane complexes that Sam talked about. And these will be codimension 1 cube complexes, so their dimension will be strictly smaller than the dimension of X, in that if you take the maximal dimension cube, it will be strictly smaller than the maximal dimension cube of X. So the hyperplane complex, by induction then, we can assume it's virtually special. So like the base case would be, zero dimensional, then it's just a bunch of points. Okay, that's trivial. So let's take a one-dimensional thing, that's just a graph. The hyperplanes there are just points. So those are both kind of trivial cases. A free group is fundamental group of a graph is a free group. Those are special automatically because their hyperplanes are embedded and they satisfy all these non-osculating conditions. So the two-dimensional case, I guess, would be the first non-trivial case. There, the hyperplanes are one-dimensional. So if you had a cat0 cube complex, cat0 square complex, its hyperplanes are graphs, and so those are known to be special already. So that's sort of so it's really the base cases are kind of trivial here. So what we can do then is apply the weak separability theorem to conclude that under these hypotheses that there exists a normal subgroup of G and an induced covering, so G double prime normal in G. I'll call G mod G double prime script G, and G X tilde, the universal cover of X mod G double prime, I'll call script X. So this covering space has two-sided acylindrical compact hyperplanes. So let me try to give an indication of what that means. So I think I'll brush over what the acylindrical hypothesis is. I might make a comment about it later. But let's just think about a very simple example. So let's take a genus genus 2 handle body, and I'm going to draw it in a little in a way that let's think about taking a punctured torus and crossing with an interval like I just did the suture manifold. That's just a genus 2 handle body. And so I can take a cube complex there, which will be, so now this is kind of thickened up. So I can take some arcs sitting on side of there. Let me draw it like I had before. Sorry about that. So this is topologically just a handle body. So I can take a curve there, and then I can take some curve here, and then when I cross it, whoops, it gets so each arc inside of the punctured torus, when I cross it with an interval, gives me a disk. And then there'll be one that goes around like this or something. I'm not going to draw the entire thing. So so this is just a surface. I'm just take the boundary of that. So there's a covering space of this that has, I'm claiming there's an infinite covering space of this that has with a preimage of these walls are already embedded here, so it's easy, but just pretend they're immersed. That I claim you can find a covering space of this surface that looks something like this. So if I take a torus, I can sort of think of the punctured torus as like that, and I've thickened it up. So there's a torus, and I puncture a hole in it. And the boundary component is a wall, and then you have these other walls like this. Let's think of this, or maybe I'll draw a hexagonal torus. So then I can take a covering space, so maybe it looks like this. If you take, say, an abelian cover of the torus, then it might look something like this. So then all these walls will be, so these guys are walls. This is the whole of the torus. And then there's these walls here. So this is just sort of a toy model. This is not literally, although you could apply this theorem to this case. So it's probably not going to give an abelian cover. Just to keep something in your mind, think about this covering space of this surface. Now I'm drawing it sort of thickened up, three-dimensional, but it's really just a two-dimensional surface. So that's the kind of picture I have in mind. So we've passed to this infinite covering space where all the preimages of the walls, it's a normal cover, it's a regular cover. Like here, the covering translations are z squared. And so that the walls here all lift to embeddings up here. Now they're already embedded down there, but I was just, I'm not a good enough artist to try to draw something immersed that would lift. But I claim that using this weak separability result, it's a standard sort of method going back to Peter Scott, that this sort of separability result allows you to lift immersions to embeddings. But the fact that it's only weak embedding means that this cover might be infinite cover. If it were a finite sheet of cover, we'd already be done, because now we have these embedded hyperplanes corresponding to these, well, in the three-manifold case, they correspond to embedded surfaces then, and we would have produced a Haken cover. Well, we actually want to prove it's virtually special, but then applying Donnie Wise's theorem again, we can conclude it was virtually special. But generic these hyperplanes in this covering space will generally not be separating if X is not Haken. Like in this case here, like this hyperplane here is not separating because I can go around there to get to the other side. So that's a key point here. Well, it's not that important, but it's just something to observe. So now in this covering space, so there's where I just used the inductive hypothesis here. And so the rest of the argument will I don't need the inductive hypothesis really again. So now we'll define the crossing graph. Let gamma of X be a graph with vertex set the walls of this covering space, the hyperplanes of this covering space, and the edges. I'll have two edges if the two walls cross each other, or if there's an essential cylinder going between them. But let's ignore this for now. So let's assume that there's no sort of essential cylinders, just for simplicity. So in this covering space here of this surface, there's all these walls here, so I'm going to get a vertex. Let me get these colors. So I'll draw. I'll just draw I'll draw all the vertices. So there's a vertex here. There's a vertex here for each of these walls in this covering space. And I'll draw an edge between them whenever the two walls cross. So this wall and this wall cross, so there's an edge there. This wall and this wall cross, there's an edge there. These guys cross. This crosses here, etc. So so here you just see like a some graph like this. And I think I probably should have had one here too, so that you would actually see. It actually, in this case, it will turn out to be a triangular graph. Where the edges are subdivided. So it's something like this. Okay? So that's the crossing graph. I was drawing them superimposed, but obviously it's just an abstract graph. So now there's a coloring space of this gamma. So if I have a graph gamma, let Cn of gamma would be the colorings, the end colorings of the graph. So when you color a graph, so actually the numbers 1 through n will be important, but I'm calling it coloring because there's this notion of coloring a graph where you're allowed to color the vertices, but if they're joined by an edge, they have to be colored different colors. Then it's a coloring of the graph. So for all pairs of adjacent vertices in the graph, the colors have to be distinct. Or if you have two walls that are crossing each other, they have to have different colors, in other words. So I regard Cn of gamma as a closed subspace of this Cantor set, just the set of all colorings of the vertices. N to the gamma, to the V of gamma, is just an infinite product of point sets, n point sets. Chekhov theorem says that's compact. It's just a Cantor set, it's totally disconnected. So I can regard Cn of gamma as a subset of that Cantor set. Now, if the degree of gamma is less than or equal to k, then I can color it with k plus 1 colors. So like this graph over here, the degree is at most 6, so I can color this with 7 colors. So how do you prove that? Well, I choose some ordering on the vertices. I color the first vertex randomly, one color. The next vertex, I color it randomly a color that hasn't been used by its adjacent vertices. But every vertex has degree 6. There's always a 7th color that's not used by one of its 6 neighbors. So there's always, so I can color the graph iteratively. Now, why do I care about graph coloring? So let me just say a few words about why I want to color these things. So let's go back to drawing colors here. I can even just this is a bipartite graph, so I could even just color it like this. Now what this gives you is it gives you a hierarchy of this covering space. These are numbered colors, so let's say blue is 1 and yellow, or let's say blue is 2 and yellow is 1. So I first could chop along all the walls that are colored number 1. When I chop along those, actually in this case I turn out I just get, after chopping along the 1s, I'm going to get some pairs of pants. So I'm going to get things that look like this. And then there's going to be these blue seams going through them. And then I chop along the 2s, everything labeled 2 here, and I just get down to these things that look like hexagons. So I'm going to get an infinite collection of these hexagons, but it's a finite stage hierarchy for this covering space. Each time I'm cutting along a hyperplane that's pi1, it's totally geodesic in the cat, zero metric, locally totally geodesic, so it's a pi1 injective subspace, and I can cut along that. And I get a hierarchy for this covering space. What I want to do is I want to find a finite sheet of covering space that's Haken and therefore has a finite hierarchy. So I found this infinite regular cover that has a hierarchy. And what I'm going to do is I'm going to try to find a finite sheet of covering space that's modeled on this. So a coloring gives rise to a hierarchy of X. You cut along the walls colored 1, then the color 2, and et cetera, until you get colored N. So in the 2 coloring over there, it's very simple to see. So in the cube complex context, you have this cube complex. The walls are these hyperplanes. Does everyone understand what I mean by the walls? So this are hyperplanes of the cube complex. So Sam talked about this in his talk. And then we cut along them, and what we're left with is just links of the vertices of the cube. So if there was another cube here, these guys would be attached, but we'd have cut the hyperplanes, all the hyperplanes, abutting that vertex, and you're left with a star of the vertex. So when you cut along all these, you're just left with stars of the vertices of the cube complex script X. And I want to keep track of the residues of the colorings here. So I'm sort of suppressing the cube complex here, but really there's sort of this dual cube picture here, dual to these hyperplanes. But I want to forget about the cubes. So here I would get a star of a vertex if I were to keep track of the cubes. But here I sort of want to forget the cubes. What's really important is sort of the dual picture. It's sort of a combinatorial version of Poincare duality, a geometric version of Poincare duality. But now, what I want to do is I want to create a finite hierarchy out of this infinite hierarchy of this covering space. So what I want to do is sort of take a superposition of these guys, and I want to choose finitely many of these colored polyhedra and use them to glue up a covering space. But the problem is, so I have infinitely many of these kind of polyhedra, these stars of vertices with their colored faces, and I want to glue up a finite cover, but there's infinitely many of these. So what I want to do is produce a finite collection of them that pair up in match up in pairs so that I can glue up a finite sheet of covering space. So to do this, I need to use a little technical thing, which is a probability measure. So there exists a probability measure mu on ck plus 1 of gamma of x, which is G invariant. So I said I can color this covering space with k plus 1 colors, but this is a stronger thing. It's saying that there's actually, I can do it in such a way that there's a measure on the space of all colorings with k plus 1 colors, which is equivariant with respect to the covering translations. Probability measure means that it's a measure, it's a Borel measure, radon measure on this space that's of total mass equal to 1. That's all a probability measure means. So it's kind of a compactness theorem. The proof of this lemma proceeds by, well, you just color the vertices randomly with n colors where n is greater than k plus 1. Now the probability that two endpoints of an edge have the same color is 1 over n. Now you can produce from an n coloring, you produce an n minus 1 coloring of the vertices by setting each vertex colored n to the smallest unused color used by its neighbors. So this is kind of like the way that we k plus 1 colored. But we're doing it in a way that's sort of equivariant. Now, this no longer gives me a valid coloring. It just colors the vertices. It's not a coloring of the graph. But it's a coloring of the vertices, which is only, it's G equivariant, but it's only got this discrepancy of 1 over n. So I can produce a k plus 1 coloring by this inductive process, and I can push the measure down. So the probability that I covered the endpoints of an edge is at most 1 over n. Then you take a weak star limit of these measures, and you obtain a G invariant measure, mu, that's supported on the actual colorings of gamma. So it has 0 probability that you've colored the endpoints of an edge the same color, because in the weak star limit, 1 over n goes to 0. And so, in that weak star limit, I'll get a measure that's concentrated just on the valid colorings of the graph gamma. So that's a summary of the proof of this lemma.
What is kind of minimal assumption on x in that lemma?
Oh, x is, yeah, sorry. So more generally, this works for a graph that has a group acting, a finite degree graph. Every edge has degree bounded by k. Every vertex, I mean, has degree bounded by k. And a co-compact group action on it. So you can even just imagine like a Cayley graph of a group. This works. You can color the vertices with the most 2G colors, where G is the number of generators. 2G plus 1, I mean. And get a measure which is group invariant. So let me draw it in this case here. So here's my wall pattern. I'm not going to draw the graph. I'm just going to draw the walls. So the vertices of the graph are the walls, and then when they're crossing, there's an edge. And so I claim I can sever color this, right? So here's some 7 coloring. So I chose a color for each one so that if they cross, then they have a different color. And this is going to define a hierarchy. So I think I could first cut along, I think black in my convention was the lowest number, was number 1. So I would cut along the black first, and then I color, so I actually, did this with Mathematica. I chose things randomly, and then if it was incompatible, then I changed it. Now, here's a random 8 coloring. So 8 is bigger than 7. Now, you see there's these incompatibilities. I think the highest color is this orange color. So I see orange here, orange here. That's the color number 8. It's actually encoded in binary. So that's... so I have this random coloring. It's an 8 coloring. I want to get a 7 coloring. Well, so each guy that's colored 8, I change it to the lowest color that's unused by any of its neighbors. So like this orange guy here, the lowest color is black, it turns out, because there's no black neighbors. So I change that to black. I change that guy to black, and all the other oranges. Unless, if there was a black there, then I'd have to change it to the next unused color, which would be the color number 2, whatever that was. I'm not sure which color it is. But anyways, these all end up being black. So I switch them to black. And I produce a 7 coloring. Now you see that I have some incompatibilities, but the probability that these 2 guys are the same color is, 1 over 8. And if I were to choose some larger number of colors, that's going to be even smaller. And so as you take the coloring going to infinity, the number of these, the measure of these 7 colorings will have probability less than 1 over n on each of these edges. So you only have to take finally many edges that represent all the orbits of this. There's only finally many orbits of edges, and because of the co-compact action. And so in the weak star limit, you'll get a probability measure that's concentrated on the colorings of the graph. Okay, so that's a summary of this coloring result. And it's just a lemma, but it actually took me about 10 months or so to figure that out, because I'm not really familiar with this kind of stuff. So now that the probability measure is just an artifice to construct what I call a solution to the gluing equation. So what I want to do is I want to reverse engineer a hierarchy for a finite sheet of covering space. So I have an infinite hierarchy corresponding to this covering space X. I have this, for each coloring of X, I get this associated hierarchy, cutting it up into these polyhedra with a color residue on their faces. So the probability measure allows me to extract some kind of finiteness associated with this hierarchy. Namely, if I take this measure, then for each of these polyhedra here with the associated colorings, there's some, so like this coloring here, there's some measure associated to this. There's some number associated, which is the probability that this guy is colored this in my probability measure. So there'll be finally, so for this particular polyhedron, there'll be different ways of coloring it. So maybe I'll draw a couple other possible colorings. So this particular guy here, this hexagon, it'll have different ways of colorings. So maybe it colored like this for some choice. And so there'll be there'll be finally many ways of coloring because it's only finite-sided. And each one of these, there'll be a number associated to it, which is the probability that that coloring appears in my probability on the space of all colorings. So this is some polygon here, which is I don't remember which one I was choosing, but this is like, let's call this P1 here. So this is P1, and P1 is adjacent to it. There's a polyhedron here in X that's adjacent to it. And this guy will also have a number of ways of coloring it. And some of these colorings of P2, so P2 is like a hexagon like this. Some of them will be compatible with this guy. So maybe it's to be compatible, they're, P1 and P2 are glued together in this covering space. So if they're compatible, then these two edges correspond to this wall, so they have to be colored the same, and these two guys have to be colored the same as well. So this guy will be compatible with this one, but this guy won't be compatible with, say, this one or this one, because this edge here is colored blue and not yellow. So I get finally many so I take one orbit representative of each of these polyhedra, so I just take finally many of those. I take all possible colorings of them, and then I look at how they're glued together inside of X up to the action of the covering translations, and I get what I call the gluing equation. So I can glue them together if their colorings match up sort of locally. Now, there's actually a refinement of this you have to do, but maybe for the sake of time, well, let's see, I have 15 minutes. So the point is that the probability measure, so I have some probability that this guy occurs, but now I haven't drawn the rest of the colors here, so there might be different ways of coloring these guys which are still compatible with the coloring of this one. There might be like that. There might be another one that looks like, so we have yellow, blue, blue again, and now maybe this guy is red and these two guys are yellow. So both of these P2s will be compatible with this P1. So the gluing equation, so I let P be the stars of vertices of X. I'll call it, so these are the polyhedra, and F is the facets of these polyhedra. So in this case, it's just the edges of those hexagons. And each of these are sort of dual to one of the edges of the cubulation of X, but I'm sort of suppressing that here. And then so each face will be contained uniquely in two different polyhedra. So here I guess I draw pentagons, but over there they're hexagons. And there's a unique polyhedron and facet, up to this covering translation. So I'm going to refine the colorings of the walls now, where I look at decreasing chains of colors emanating from a vertex. So if I have a vertex here, and two different colorings, then I say that these guys are the same color if all the smaller colors the smaller chains of colors coming out of that are the same. So here they're the same. All the smaller chains are 1 here. There's a 1 here. This adjacent guy is different on this. It's 3 here and 4 over here. But those are larger colors, so they don't affect the supercoloring. And if I looked at, let's see, I guess the 3 here and the 3 here will also be supercolored the same. Well, we haven't drawn enough of the graph, but anyways, all the adjacent guys are 2, and I have to go through all decreasing chains through here. So there might be some 1s over here that would have to be compatible on both sides. So so that's what we call the supercoloring, and then the variables for the gluing equations will be supercolored polyhedra. And the gluing equations will say that for a given supercolored face, the supercolored polyhedra P1 has to induce, which induces the coloring of F, must be the, equal to the supercoloring of P2, which induces the supercoloring of F. So if you look at a face F here, like this face here, F, then the supercolorings of it will sort of be determined by some finite amount of data inside of the covering space X. And we want all the polyhedra at P1, so the number which induced that supercoloring of F to be the same as the polyhedra P2, colored polyhedra, which induces the supercoloring of F. Everything's equivariant, so I insist that the solutions to these equations should be G equivariant. So you get one solution to the equation from the probability measure. So the G invariant measure mu gives us a solution to the gluing equations with non-negative weights. And then you take an integral solution. So it's a finite set of integral equations. You have one positive solution, and then you can get an integral positive solution. So first you get a rational solution, and then you clear denominators with non-negative integral weights. So this is a standard thing in like polyhedral geometry, or in the simplex method, or when you're studying equations with rational coefficients, then you can always get a rational solution. So the coloring measure was just an artifice to give you a solution to these gluing equations, and then you get finally many of these colored polyhedra, and now they have the property that they all match up in pairs. So I take this integral solution of polyhedral gluing equations, and now I glue up a finite sheeted cover of X, which is modeled on the hierarchy of this colorings on this infinite color space, covering space script X. So it's gluing up sort of inductively. So you construct a sequence. It's usually disconnected of finite cube complexes nu J with a certain boundary pattern of colors, colored 1 through J, which has the following properties. There's a locally convex immersion from Vj into X. So the first Vk plus 1 will be just this disjoint collection of these supercolored polyhedra that we got from the solution of the gluing equations, the integral solution. So it's just disconnected set of polyhedra. And then we glue them together along the k plus first color. So Vk is obtained from Vk plus 1 by gluing all the k plus 1 colors together in pairs. Because they satisfy the gluing equations, we can glue them together in pairs so that the faces, the supercolorings of the faces match up. When you glue the k plus 1 guys together, everything else will match up because of our so the supercoloring may have seemed kind of arbitrary, but it's set up in such a way that when you glue up two polyhedra so that the facet has the same induced supercoloring, then all the facets crossing through that, because the crossing graph will be induced to the same color, because they're smaller colors than the one that we're gluing together, which is the highest color k plus 1. So you proceed inductively this way. And all the multiplicities of the g orbits of the colored polyhedra making up Vj will satisfy the polyhedral gluing equations. And the boundary of Vj is a union of facets containing precisely one polyhedron. So when you're gluing everything up in pairs at each stage, so what's the boundary will be all the facets that haven't been paired up at the jth stage. And the boundary pattern of the ith boundary pattern will consist of all the facets which are colored i's. So there's sort of a compatible coloring. So the supercoloring guarantees when I glue colored polyhedra P1 and P2, it's exactly what I was saying before. If I glue these guys together, then all the colors of the guys crossing it will match up. So maybe k plus 1 is, let's say it's 3, and then these blues guys are 2. So a 2 here will get glued to a 2 here because this wall crosses through this wall here. And so by the supercoloring, these guys will have to match up in pairs because there's smaller colors that cross through this guy. So the supercoloring is set up in such a way that when you glue things together, it's sort of like Legos. You glue them together and all the colors match up nicely. So when I glue, here's another picture. So I glue P1 to P2. These guys are labeled 4. Then this guy crossing has to be colored the same one as this guy because they're smaller than 4. And this guy are smaller. In each stage, you have already glued up all the colors that are bigger than 4. So there might have been some other guys from previous stages that are present here But when you glue them together, those guys don't necessarily, the higher colors don't have to match. So the base case is this collection of polyhedra. You keep gluing them together. Now, there's an issue that when you want to glue the I plus first boundary pattern at the I plus first stage to get the ith stage, everything matches up in pairs, but it turns out they're coverings of a fixed complex. They don't match up as isometrically. So you have to apply Wise's theorem again to pass to a further covering space in which everything matches up in pairs isometrically. So that's I'm using Wise's theorem again there. And the cube complex V0 will have no boundary pattern. It'll give a finite sheet cover of X, which has, by construction, a malnormal quasi-convex hierarchy. One more application of Wise's theorem gives a covering which is special. So that's sort of a summary of the proof. So I told you really all the ideas that go into the theorem. Whether or not I've told them clearly is another matter. But anyways, this is sort of a summary of the proof and really all the critical ideas that go into this theorem. So let's see. I wanted to mention in the last 5 minutes. I wanted to mention a few open problems. I wanted to mention the non-hyperbolic case. So questions 15 through 18 from Thurston's problem list also have extensions to non-positively curved manifolds. So it's a recent theorem of Shizitsky and Wise that a compact 3-manifold emits a non-positively curved metric if and only if it's virtually special. Now there's a caveat that it'll be special acting on a cube complex with finitely many hyperplanes, but it might be non-compact rather than compact like in the hyperbolic case. So it's virtually non-compact special potentially. But it still has finitely many walls, so it still gives you, by speciality, it gives you an injection into a right-angled Artin group. Now Lieb has determined which aspherical 3-manifolds are non-positively curved. The only exceptions are certain graph manifolds. So in particular, this implies the virtual Riefers condition, therefore virtual fibering. It implies linearity of the fundamental group, etc. All these conditions here. And for non-positively curved graph manifolds, this result is due to Yi Lu, 2011. The manifolds are not necessarily Lerf, but they are sort of Q-surf. If you look at the right, you have to look at the right set of subgroups to be quasi-convex. Quasi-convex inside of the right-angled Artin group that everything injects into. Okay, so I wanted to mention in the last few minutes a few open questions. So there's an interesting question of Long and Reed. Can two compact 3-manifolds have fundamental groups which are not isomorphic but have the same profinite completion? This question is equivalent to saying, given two 3-manifold groups, if they have the same collection of finite quotients, then are they isomorphic? So the conjecture here is that they are isomorphic if their profinite completions are the same. Anyways, it's a fact that if you have two finitely generated groups, their profinite completions are the same precisely when they have the same collection of finite quotients. So if you had two knots that, for example, that were not diffeomorphic, they're not the same knot, then there would be two finite quotients of the fundamental groups that one which is a finite quotient of one knot complement group, but not the other one, for example. Are compact 3-manifold groups linear? So the only case left are these graph manifolds, which are not non-positively curved by the theorem I just mentioned. So these graph manifolds are not known to be have linear fundamental group. There's a question of Cooper. Is there an R? So a hyperbolic 3-manifold with injectator radius greater than R is Haken. This method of Kahn and Markovich produces highly immersed surfaces. So anyway, so this was an interesting possible approach to the virtual Haken conjecture, but it sort of hasn't panned out yet. But I think it's still an interesting question that proof of the virtual Haken conjecture sort of has no bearing on it. Another interesting question is define a bound on the index of a cover in aspherical 3-manifold, which is Haken. So of course this is only mainly interesting in the hyperbolic case. But the bound should be some computable function of some complexity of the 3-manifold, such as the minimal number of tetrahedra of a triangulation or some other complexity. Then there should be some computable function that tells you how high an index cover you need to get something that's Haken. But the proof is so complex. I mean, Wise's arguments especially are hundreds of pages, and it's really hard to extract explicit estimates out of all that. There's a question of canon. If you have a hyperbolic group whose boundary is a two-sphere, is it virtually a Kleinian group? So it's known that if you have a co-compact lattice in hyperbolic isometries of hyperbolic 3 space, then it's a hyperbolic group whose boundary at infinity is a two-sphere. So Cannon's conjecture is the converse of that. So recently Markovich has shown that it suffices that for any points in pairs of points in S2 to find a quasi-convex surface subgroup whose limit set separates the pair. So if you could generalize Kahneman-Markovich's argument to this abstract context of a hyperbolic group with boundary of two-sphere, then that would give a possible approach to this Cannon conjecture. The problem is that Kahneman-Markovich make strong use of the ergodicity properties of geodesic flow on a hyperbolic 3 manifold that no one's figured out how to carry over to this context yet. Here's another question. For two hyperbolic 3 manifolds, is there a finite sheet of cover M1 prime of M1 such that there's a non-zero degree map to M2? Some of you might have heard of this Ehrenpreis conjecture that Kahneman-Markovich resolved that says that if you have two surfaces, they have a common covering space. They have covering spaces which are epsilon by Lipschitz maps between them. So you can't hope for that for hyperbolic 3 manifolds. There's incommensurable hyperbolic 3 manifolds. But you can ask for whether there's a non-zero degree map from some cover of one onto the other one. And you can also ask, is there a map which preserves the fibering, for example? So I have no idea about answers to these questions. Here's a weird question. Do hyperbolic 3 manifolds contain an immersed quasi-Fuchsian surface of odd Euler characteristic? A closed surface. So Kahneman-Markovich produced orientable surfaces. This would have to be non-orientable. This came up in some question I was thinking about, but and then Nibble and Wise ask which 3 manifold groups are Lerf. They conjecture that it's Lerf if and only if there's no Seifert to Seifert gluing in the JSJ decomposition. So every Seifert piece has to be adjacent to some hyperbolic piece in the JSJ decomposition, if you're familiar with that. So those are some interesting questions that are still left unresolved. They're probably not as important as Thurston's list of questions, but anyways, I wanted to dedicate these talks to the memory of Bill Thurston, who just, as you probably know, he passed away just last month. And so all this, of course, would have been impossible without his insight. So thanks.